also talk to us because we're also like in need of some speakers. Okay, cool. So today we have Carl Doersch. He's from the ML department. Is that right?
Yes.
Okay, he's from the ML department here, and he's going to talk about some problems in computer vision.
Right, so you don't see me that much because this is joint work with Abhinav Gupta, who's in the Robotics Institute, and Alyosha Efros, who's now at UC Berkeley. So that's where I was all spring. So the goal of this talk is to do visual data mining. That means that we start with a huge set of images and potentially any metadata that we can find along with those, like GPS labels or web text. And our goal is to mine out things like this, these sets of patches that depict the same thing. Now, this is a hard problem because in vision, we don't have any good way of telling whether two patches actually depict the same thing. And on top of that, we have a hard search problem. So the way that machine learning tends to approach this sort of problem is to label a bunch of examples of all of these things and then train a classifier. But we're not going to assume that we have labels like that. And there's a number of reasons for this. First of all, unlabeled data is much cheaper than labeled data. The largest public labeled data set that we have available to us is ImageNet, with 14 million images. But Facebook has about 250 billion images, which were just uploaded by their users, don't have much information associated with them. But you might wonder if 14 million labels is even necessary. After all, we didn't need 14 million labels in order to learn to see. From a more machine learning standpoint, it's also not necessarily clear what we should label in these images. So one useful thing that you might want for representing a data set is to detect people. But so the way you would do this in machine learning is to train a classifier with humans as positive images and non-humans as negative images. And say we train this with empirical risk minimization, and here is the 10,000th image that we look at. So at this point, the algorithm already knows what people look like, and in particular their faces, because faces are easy. So this image contains a face, and so the algorithm gets this image, says it contains a face, says there's a person, so there's no error, and it doesn't learn anything. Now, this seems kind of unfortunate, because there's actually a lot of unusual stuff about this image. I mean, how often are you going to see the soles of somebody's feet? So even if we have these labels, it might be a good idea to treat this as a visual data mining problem to mine out those small things that will help us when the easy stuff is occluded. So in this work, we focus on what we call mid-level visual elements, or mid-level discriminative patches. So there are sets of patches like this, depicting something which is frequent, i.e. we can find many instances across our data set, and they're informative in that they tell us something about the scene. And we're going to measure this second part using our weak label. So in the case of humans, the feet and hands will tell us that there's a person in the image, and we can use this to tell whether we've actually found one of these elements. So if we want to actually build a classifier, or build an element like this, we need some way of representing it. And we're going to use patch classifiers to do this. So if we have an element like this one, we'll assume there's an associated patch classifier where we can extract patches from this image and then label them with yes or no, does this contain the element? So these patches don't, and we'll slide along until we get to this patch, at which point, hopefully, we'll say yes. So if we want to train a classifier to do this, we need some labeled data. And unfortunately, as I said, our labels are weak. So we may have something like this image contains a horse or doesn't contain a horse, or maybe something even weaker, like things we can get for free, like geotags, like this image comes from Paris, this image doesn't come from Paris. So the simplest approach to dealing with this is to just label all of the patches from the positive images as positive examples and train a classifier. But the problem is that there's about 10,000 patches per image, and the vast majority of them are unclassifiable, like these trees. So if we try to train a simple classifier, there's going to be too much variety, and it's going to underfit. And if we try to train a complex classifier, well, it's going to try to learn everything. It's going to end up with a very high variance representation, and it's going to probably also be very computationally expensive. So in some sense, our classifiers need to choose their own data as they're going along. But that seems like a very difficult and under-constrained problem. But keep in mind that all of these patches are going to be similar. We assume that we have some distance metrics that we can use to measure and find a set of similar positive patches that we can use for our initialization. So this implies or suggests a sort of clustering approach. But we don't want to use a standard clustering algorithm like k-means because we don't actually want to force everything into a cluster. There's going to be lots of garbage patches that don't really fit anywhere. And if we try to partition the whole space, we're going to put these into potentially good clusters and pollute them. So to find an algorithm, a clustering algorithm which doesn't partition the data set, we're going to start with mean shift. Now you've probably heard of mean shift, but I'll just recap it quickly. The way it works is that you first choose a point in your data, then you draw a circle around that point, and this point is going to be your centroid. Once we've drawn the circle, we average everything in the circle to get the updated centroid, and we move to that location. And then we repeat this process until we've converged to some local maximum. So the nice thing about this algorithm is that to define each of these centroids at their convergence point, we only have to pay attention to the data that's within that small circle, which means that the outliers in the data set don't actually influence these clusters. Another way of looking at mean shift is to view it as first forming a kernel density estimate of the data, and then finding the local maxima. So this raises the question of whether this density is actually a meaningful object in patch feature space. And unfortunately, the answer is no. So here's an example. Here's a patch, and here are its nearest neighbors. This is a great element, especially if we want to, say, describe Paris architecture. And here's the minimum distance to all of these patches from that center patch. Here's another patch, and here are its nearest neighbors. This is not going to be a good visual element for any purpose. There's multiple semantic concepts in these nearest neighbors. Yet the max distance to all of these patches is less than half of the value that we saw above. And this may not seem like that big of a difference, but we're using hog features to get these nearest neighbors, and that's a 2,000 dimensional descriptor. So in 2,000 dimensional feature space, the actual volume occupied by all of this stuff, in the case of the bottom, is 1 over 2 to the 2,000th power of the volume occupied by nothing in the case above. So really, our feature space looks something like this, where we have dense clusters for the very frequent common elements that we don't really care about representing. There's going to be dense clusters for the sort of irregularities of the feature space, and maybe less dense clusters for the elements that we actually care about. So this is where we're going to use our weak label. Remember that we have a negative set, which we can assume has the same sets of common elements, the same irregularities of the feature space, but has fewer instances of the elements that we actually care about. Now, note we're making a weaker assumption than we usually make for labels. There can be the same thing that has different labels. We can have even instances of the elements that we care about occurring in the negative set. All we're assuming is that there's going to be less of the things that we care about in the negative set than in the positive set. So we can estimate a density now for this negative set. And bringing back our positive density, we can divide those two to find the density ratio. And there's been a fair amount of work on density ratio estimation previously, and so we're just sort of adapting those ideas to our problem. So you can see that this density ratio is picking out exactly the region of the space we wanted. But there's another issue that we've introduced here. These clusters all started off their lives as Gaussians. But after doing this division, you can see that we've developed all of these weird spurs. The reason this happens is that we're dividing by an estimate of this, the negative density, which we assume is going to be very low in these regions where there's not many negative patches. Dividing by a reasonably high variance thing that's going to be small is going to produce an estimator that has very high variance. So to deal with this, we're going to use an adaptive bandwidth. Specifically, we're going to use a large bandwidth for our kernel density estimate in the regions where we have few negative patches, and a small one in regions where we have lots of negative patches. So to summarize, we're going to find the local optima of an estimate of the density ratio, and we're going to allow an adaptive bandwidth. And one thing that I've kind of swept under the carpet, we need to be extremely fast in this procedure. We want to ideally have just one pass through the data, because with 10,000 images and 10,000 patches per image, we have 100 million patches, and that doesn't fit in memory. OK, so now I'm going to dive into the math. And the reason I want to go into the math is that at the end, you're going to see a pretty interesting connection to support vector machines. So here is the standard density estimate that you optimize in mean shift. For the point W, that's where we're doing the estimate. We want to maximize with respect to W. We're computing the distance between each patch feature and that centroid, and taking B minus that value and max with 0. So what does that mean in pictures? So here's the W point where we're trying to estimate our density. We go through all of our data points, and for each one, if it's exactly at W, well, we get a reward of B. As the distance increases, the reward diminishes until we get to that distance of B. And then from that point on, it adds 0 to our estimate. This is the standard triangular kernel. Now, we want to use a adaptive bandwidth with this. So we change that constant lowercase b to be a function of W. And then we only want to maximize with respect to the positive data divided by the same estimate for the negative data. So now this is an estimate of the density ratio. So to choose our capital B of W, we're going to use this. And we're going to choose this in kind of a tricky way so that we make our lives easy. You'll notice that this expression was copied from the denominator. So when we make this constraint satisfied, it means that we're fixing the value of the denominator to be equal to this constant beta. And of course, because we're using the same bandwidth in the numerator and denominator, we're still going to have a valid estimate of the density ratio. Right, so we're going to increase the bandwidth if the denominator produces a value smaller than beta, and decrease it if it's larger than beta. So that means we can, because this is now fixed to a constant, we can ignore it and switch this to be a constrained optimization problem. All right. Right, so now we have a constrained optimization problem, just replacing capital B with the lowercase b that is going to keep our constraint satisfied. Now we need to make a choice for the distance function. And for us, we're going to use normalized correlation, because first, it's a good distance metric. It's used frequently in vision. But also, when we use this distance metric, we can rewrite, with a little bit of algebra that I'm not going to go into, we can rewrite it in this form. And now you can see that it actually looks pretty similar to a support vector machine. So to build on that analogy, here's some toy data. This constraint here is putting a constraint on the sum of the distances between the hyperplane and those distances. So this is exactly the margin that a soft margin SVM would be penalizing. But we just use a hard constraint rather than a penalty. Now for the positive data, we're again rewarding the sum of the distances between the positive data and the hyperplane. But here's where the big difference is between SVMs and us. We're only focusing on the things that are on the right side of the hyperplane, whereas the SVM would be putting a penalty on all of the positive data that's on the negative side of the hyperplane. So this is why our algorithm is so fast. All of this negative data can be ignored when we're doing this optimization. So we basically just mine through the whole data, looking for patches that occur on the positive side of the hyperplane, and throw away everything else. All right, so that's the formulation. Now I'm going to go on to some results. So if we apply this to data where the positive set comes from Google Street View in Paris, and the negative data comes from other cities in Google Street View, we get the following elements to describe Paris. Now, we're not the first people to tackle this problem, but I would argue that we are doing it better. And to show this, we're going to use a purity coverage plot, which is analogous to a precision recall plot, but extended to weakly labeled data. So here's how we construct that plot. Remember that we have a classifier associated with every element. So we get a classification score for each patch. So we can rank our patches based on that score. And then we just walk down the ranking. The purity is going to be the fraction of positives that come before that point in the ranking. And the coverage is going to be the total number of pixels that contribute to at least one of these patches. So when we make a mistake, we don't get any additional coverage because it's, we're only caring about the coverage for the positives. So the purity drops, we don't get any additional coverage, and then we continue down the ranking like so. And of course, the coverage for multiple elements is just going to be the union of the coverages for all of those elements. So here's the results, and I have more details in the paper on exactly the analysis that we're doing here. But the algorithm, as I've described it thus far, is the yellow curve. The pink curve is an additional sort of deduplication step so that you don't have too many elements representing the same thing. And these other curves are showing the benefits of various components of our algorithm. So if you start off with just a patch and its nearest neighbors to represent your elements, you get the blue curve. If you allow for some optimization, you get a better result. And if you use support vector machines to do a better job modeling the relation between the positives and negatives, then you get the black curve. The other evaluation that we use for this algorithm is the standard problem of image classification. So we chose the dataset Indoor 67, which is images like these, and your goal is to classify them into one of 67 different kinds of indoor scenes. And to run our algorithm on this dataset, we first find elements for each category. So that category is positives, everything else is negatives. And then to describe each one of these images, we first build a spatial pyramid of regions, and then within each region we take the maximum response. Within each region we take the maximum response for each element, and we concatenate those into one long vector and throw that into a linear SVM. So that's a pretty standard way of going from these types of visual words representations into something that we can classify. Not really anything novel here, but yet we get state-of-the-art results on this particular data set. And all of these results are in the last 5 years. So this is a pretty challenging data set and a pretty modern data set. And of course, we get a little additional boost if we use ours in using the improved Fisher vectors, which is sort of the state-of-the-art visual words type algorithm, which has been engineered quite a bit. All right, but even beyond this, we get an added bonus for using these visual elements to represent our data. And that is that we can debug our classifications. So these two images were classified as bowling alley and meeting room, respectively. And we can then look at which elements contributed the most to the SVM score for that classification. So here's a selection of those elements that contributed a lot. And here I'm showing a heat map of where those elements occurred in the image. This can be particularly useful if you want to understand why the errors happened. So here are some confident errors that our algorithm makes. And for example, it may not be clear why this was classified as a corridor, or sorry, why it was classified as a staircase when the truth is a corridor. But if you look at the elements that it's finding, well, it's firing on the railings. So that's a staircase element. All right, so now I'm going to switch gears and talk about how we do this without labels. So remember that if we start with a patch and find its nearest neighbors, we often find something reasonably good. And that's happening in this example. But there's two problems that we have to deal with on top of this. First is that we're going to make errors in this matching, so we have to have some way of detecting those. And second, there's going to be bad initializations that will create incoherent clusters, and we have to discard those somehow. We have to have some way of measuring how coherent the cluster is as a whole. So one cue that you might think we could use if we don't have any labels is image context. After all of these cat patches are going to have eyes and noses and ears in their context, but the motorcycle is not going to have those, at least we would hope. So the simplest implementation of this is to just concatenate the features for the context onto the patch and use those to do the same nearest neighbor matching. Unfortunately, that doesn't work very well. And the reason, it seems, is that by having all of these features all together, we're now asking the nearest neighbors to match too many things all at once. And so the algorithm kind of runs out of data. And hence, these cats actually aren't all that close together in feature space, and so the algorithm makes some kind of ridiculous errors. So you can see what's going on here. When we look at the actual images that these patches came from, these eyes don't actually align that well. So instead, we're going to use the context in a similar way that we used the weak label in the first part of this talk, specifically as a way of telling whether the original ranking actually fits together. The way that we do this is to first select one of these patches and then hold out its context. And then we use the other patches in the cluster to predict what should be in that context.